Hi everyone, my name is Pradyumn Kejriwal and this is TLE Eliminators, and today we'll discuss the CF round 1002, that is Division 2, and we'll discuss the first four problems. So before we move on to that, I would like you to talk about the CP31 sheet by TLE Eliminators. So as you can see that this is a CP sheet, like it contains problems from all the ratings from 800 up to 1900, and it contains the best 31 problems that we think that would be beneficial for you. Like if you solve all of these problems of a certain rating, then we think that probably like most of the topics will be covered. So you don't need to search for problems by yourself on Code Forces. And every week we'll release 6 to 7 solution videos of these problems. So as you can see, they are coming soon. And every week we'll release 6 to 7 of them over all the ratings. Okay, so let's start. All right, so today the first problem was called Milya and Two Arrays. The problem was an array is called good if for any element x that appears in the array, it holds that x appears at least twice. For example, the arrays 1 to 1, 1 to 1, 1, 2 are good, 1, 3, 3 is good, and like all of them are good because all the elements that occur appear at least twice. Like here, 1 appears 3 times, 2 appears 2 times, etc. While these arrays are not good because in this 1 appears only 1 time, 2 appears only 1 time, and in this 2 and 3 appear only 1 time. Milya has two good arrays, A and B of length n. So she has two good arrays. She can rearrange the elements in array A in any way. Okay. After that, she obtains an array C of length n, where Ci is equal to Ai plus Bi. So basically, she can rearrange the elements in the array A, and then she'll add the elements of Ai and Bi, and she'll obtain another array which is C, which is called Ci. Determine whether Milya can rearrange the elements of in array A such that there are at least three distinct elements in array C. Okay, so the problem is like we have been given um two arrays. Okay, one array is A. So let's say it is something like this. Suppose n is equal to 5, and the other array is B. And we can actually rearrange the elements of A however we like. Okay, and then we will make another array C which contains the elements which are sum of these two arrays. Okay, so this plus this will become this element. So I think the question is clear. Let's look at the samples. All right. So yeah, and we want to print that is it possible to rearrange A in such a way that C contains at least three distinct elements. So it can't be that C has all the same elements because then it would have only one distinct element. And it cannot be that C has only two distinct elements. Okay, so it has to have at least three elements. Okay, so let's have a look at the samples. So the first sample is 1 to 1 2 and 1 to 1 2. So the two arrays are like 1 to 1 2 and 1 to 1 2. All right, so 1 to 1 2. So actually, if we just add both of these arrays like this only, then we'll get 2 4 2 4. So if this is the array C, then actually this is not a correct array because it has only two distinct elements. But what we can do is we can actually rearrange the array A. So how will we rearrange it? We can do something like let's see. We can do something like we can make it 2 1, like 1 2 2 1. Okay. So in this case, we'll get 2 4 3 and 3. So this array has at least three distinct elements. Right? So that's why the answer is yes. Now let us look at another sample, which is, let's say this one. So in this case, if you can observe that this array 2 contains all of the same elements. So if you just like if you rearrange the elements of A however you like, it won't make any difference because the array C will contain 102, 101, 102, and 101. Maybe in different order, but it will contain only those numbers, right? So um that's why the answer is no. Okay. So in this case, like what we can actually do, we can actually look at more samples. Like, okay, this is one case where both the arrays are same. I mean, both the arrays have only one element. Like, let's say one A. A has A has just like suppose 1, 1, and 1, and B has 2, 2, and 2. So in this case, it is not possible. Then let's say another case we can think about, that maybe A has all the same elements, 1, 1, and 1. Okay. And B has maybe two different elements. Two elements which are distinct, like 2, 2, and 3, or maybe 2, 5, and 2. Something like that. So in this case also the answer is no, because you will get only two different elements. Like since A is 1, 1, 1, you will get 3, 3, and 4. So there are only two different elements. Okay. But what if we have, like, let's say we have in the array A, we have all same elements, 1, 1, and 1. But in the array B, actually this is not a valid test case, because in this case 3 appears only once. So B is not a good array. So this was not a good example. Let's say we have this. Okay. So these two are good arrays, but the answer is no, because B has only two distinct elements and A is the same. All right. But let's say A has three elements. I mean, let's say A is the fully the same, and B has at least three distinct elements. Like let's say 2, 2, 3, 3, and 4, 4. So in this case, the answer would be yes. Because when you just add them in the array C also, you will get distinct elements, three distinct elements, right? So we have seen in this case that what if all the elements in A are same, right? Like if all the elements in A are same, then the number of elements in B, the number of distinct elements in B has to be at least 3, right? Is that clear? Is up till here, is it clear? Everyone who could not solve A, up till here, is that clear? That if A has all the same elements, then B has to have at least three distinct elements, so that C also has at least three distinct elements, right? So is it clear? Just write a yes or no in the chat. Okay. So now we have looked at this case where A has all same elements, and it is like the same if B has all same elements, because it is just symmetric. So, but what if they don't have all same elements? What if they have at least two distinct elements, like both array A and array B have some different elements? Okay. So we know that they are good arrays, right? In this statement, they have given us that they are actually good arrays. Good arrays means that each element occurs at least twice, right? So let's say in array A, we have at least two distinct elements, right? So let's say we have just two distinct elements, XX and YY. And in array B, we have like ZZ and WW. Okay. And there may be other elements also. Like maybe there are more X's, there are more Y's, or maybe there are more numbers in A, but which are not X or Y. But this is the minimum case, right? Like itna to hoga hi in both the arrays, right? So so basically this is the minimum case. So if in this case you are able to make like three distinct elements, then it is always possible to make three distinct elements, right? So let's say you make one, like let's say you rearrange this like XY and XY. Okay. So you rearrange the array A like XY, XY. Then basically this element becomes X plus Z. This one becomes Y plus Z. This one becomes X plus W. And this one becomes Y plus W. Right? And since we know that x is not equal to y and z is not equal to w, therefore either like in out of these four elements, at least three are distinct. X plus z. Yeah. Since we know that x is not equal to y and z is not equal to w. So actually, I'll just explain you that is an example. Okay. So we had a sample, right? 1, 1, 2, 2, and we had 1, 2, 1, 2. I mean, okay, 1, 1, 2, 2 also in that case. 1, 1, 2, 2. So if we rearrange this A, like if we rearrange it like 1, 2, 1, 2, and here we rearrange it like we don't change it. Actually, we can't change that also. So we rearrange it like this. That this is A and this is B. Now if I make the array C, then it is like 2, uh, 3, 3, and 4. So therefore we got like four distinct elements. I mean three distinct elements. Because this 2 plus 1 and 1 plus 2 became the same. Alright. So that's what we can actually do. That if there are at least two distinct elements in both the case, like in both the arrays, then we can actually shuffle it like this, that x, y, and z, z, w, w. Then out of these four, at least three will be distinct. And why would they be distinct? Like, how can I prove that? I can prove that because this is not equal to this, and this is not equal to this. And also, what we can say is this is not equal to this. Because basically, if these two, like what I am saying is, if these two were to be equal, then x should be equal to y. But x is not equal to y, right? And if these two were to be equal, then z equal to w होना चाहिए था. But that is not the case. So these two are not equal, these two are not equal, and these two are not equal. And also these two are not also equal. So there can be at most one equal pair. Like this one, like these two can be equal, but nothing more than that. So there are at least three distinct elements. So, so basically my point is that if both the arrays have at least two distinct elements, then we can always make an array C by changing them like this, by rearranging the array A like this. But let's say we had some more elements, then we can just put them anywhere we like. We just care about these four, because by using these four we get these three distinct elements or four distinct elements, and maybe the rest of them also give some other elements, but at least three we get, right? That's my point. Like for example, if we have something like 1, 1, 2, 2, and 1, and we have 3, 3, 4, 4, then this one is extra. Sorry, this 4, 4, and 4. So these 1 and 4 are extra. So we don't care about them. We'll just rearrange this 1, 1, 2, 2 to like 1, 2, 1, 2. Okay. So if we do that, 1, 2, 1, 2, and if we take the sum, then these four elements, like the four elements which will come here, they will contain three distinct elements. So if you can't see that, like this will be 4, this will be 5, this will be 5, and this will be 6. So these four elements contain three distinct elements, and so we don't care about the rest of them because we need at least three, right? So that's why the answer is yes, if both the arrays have at least two distinct elements. Okay. And if they don't have at least two, then we already saw the case that if one of them has all equal elements, then the other one has to have at least three distinct elements. So is that part clear? Like if someone has a doubt, I'll explain again. I'll explain in a better way, maybe slowly. So if someone has a doubt, they can ask. Like in my approach, if they have a doubt. So you all don't have a doubt? Clear. Okay, so someone is asking that it is written that we can rearrange A in any way. So he sorted A and did AI plus BI. So why is it wrong? It is wrong because like that doesn't mean that you cannot make. Like I would have to think about a test case for this. Like let's say we had two. This is 5 5 4 4. So like suppose A is given to be this and B is given to be this. Okay. Then you are just adding them up. Like you are sorting this A. This is already sorted. So 1 1 2 2, and you are adding them up. You are saying that this is 6 6 6 6, right? And then you are saying that this has only one distinct element. This C becomes this, and it doesn't have at least three distinct elements. So the answer is no. But in this case, the answer is yes, because you can rearrange them. Like you can rearrange A like 1 2 1 2, and you will get three distinct elements. So it's not always optimal to sort. Like why are you sorting? Sorting does nothing. Like in this case, this is the optimal approach. Sorting is not optimal. So that's why you are getting wrong answer. Okay. Anyway, so I'll show you the code quickly for this one. I just use a set. Pairwise swapping. You don't need to actually make the array A. You can just follow my logic that if both of them are at least two distinct elements, then the answer is yes. And if one of them has only one distinct element, then the other one should have at least three. So actually, this condition is very nice. That see either what should happen, that either distinct elements in A should be greater than or equal to 2, and distinct elements in B should be greater than or equal to 2, or uh, dA equal to 1, then dB should be greater than or equal to 3. So this just means like both of these actually say, we can actually say that dA plus dB should be greater than or equal to 4. So that's why that's what I did. Okay, so I just counted the number of distinct elements in both the arrays, and then they should be greater than or equal to 4. Okay, so yeah, I input like this is int and cnn, and I inputted both the arrays. Okay, and I made two sets s and t, and I just like this set s contains all the elements in A, and t contains the elements in B. So if s dot size plus t dot size greater than 3, then the answer is yes. Otherwise, the answer is no. Like greater than 3 is the same as greater than or equal to 4. Okay. So that's what I did in problem A. So is it clear, everyone? Yes. S into t greater than or equal to 3, then it's true. S into t greater than or equal to 3. Yeah, true. That also you can do. True. Anyways, so let's move on to the problem number 2. That is cost of the array. You are given an array A of length n and an even integer k. You need to split the array A into exactly k non-empty subarrays such that each element of the array A belongs to exactly one subarray. So we need to, like, we have been given an array A. Okay, so there's an array A. Let's say we have A1, A2 up to AN. A1, A2, A3, or let's say A4, A5. Okay, and an integer k we have been given, and we need to divide these. Suppose we k is equal to 2, then we need to divide this array into like two groups. So this is one group and this is another group. These two groups we have, and each element should be in at least one group, and all the groups should be non-empty. Like we cannot have empty groups. Okay, so that's like we have to split the array A into k groups. Next, all the subarrays with even indices, second, fourth, up to kth. Like in this case, this is the first group, second group, etc. So the second group are concatenated into a single array B. So we make a single array B out of all the even groups. So A4, A5, and maybe if K was equal to like larger, 4 or 8 or 10, then more even indices would be there. So we'll concatenate all of them. After that, 0 is added to the end of the array B. Okay, so for example, so yeah, I'll take an example. So let's say in this case only we had K equal to 4. Okay, so we need to make 4 groups, right? So if we like make groups like this, one group is this, second is this, third is this, and fourth is this. So this is first group, second group, third group, fourth group. So if we concatenate the even groups, so it will become like the array B will become A3, A5, and in the end we concatenate a 0. So this is the array B. Okay. Now the cost of the array B is defined as the minimum index I, such that Bi is not equal to I, like one indexed. Okay. For example, the cost of the array B is 3 because 1, 2, 4, 5, 0. So 1 equal to the index, there is 1, 2 equal to index 2, but 4 is not equal to index 3. So the cost is 3. Okay. Determine the minimum cost of the array B that can be obtained with an optimal partitioning of the array A into subarrays. So out of all the partitions that we can do in array A, we want to find the minimum cost of the array B. And cost is defined as the first index such that Bi is not equal to I. Okay. So the problem should be clear that we make an array B, we need to find the minimum cost out of all the possible arrangements. All right. So how do we do this? Like, first of all, the thing is that we need to find the minimum cost. Let's just look at samples. Okay. Let's look at this one. 5, 4, 1, 1. So K is equal to 4. And we have 1, 1, 1, 2, 2. Okay. So we actually have to make an array B and we have to minimize its cost, right? So basically for the first index, like suppose this is the array B, we are making the array B, right? So the first index is here. Now if on the first index, the first element, this is A1, if it is not equal to 1, if A1 is not equal to 1, then the score is 1, right? Like the cost is 1. And we need to minimize the cost, right? So if we can do that, like if we can make this element not equal to 1, then we'll actually do that, right? If it is possible that this element is not equal to 1, then we'll actually make it not equal to 1. Like we'll put something else right here. Okay. And then the cost would be 1. Otherwise, the cost will be greater than 1, right? Because it is the first index that is not equal to the element. So K is equal to 4, right? So and N equal to 5 here. N is equal to 5. So what does that mean? That basically in all the groups there will be one element, and in one of the groups there will be two elements, right? So let's say these two elements, I'll choose another color. Wait. So let's say this is one group, this is one group, or okay, this is one group, this is one group, this is one group, and this whole is one group. So we have 3 groups of 1 length and 1 group of 2 length. So like, as you can see that the number of groups is 1 less than n, right? It is like 1. N minus k is 1, right? So that's why we need one group of 2 size and other one of 1 size, okay? Now what we are trying to do is that I am trying to put something here which is not 1, okay? So basically first element will always go to array A, right? I mean, see, what we are actually doing is we are taking the alternate subarrays, right? Like if we make these segments, let's say the first segment is this, second is this, third is this, and fourth is this. Then that means that we are taking this element, like this subarray and this subarray. So we are taking the alternate elements, right? That is the question. So definitely we cannot take the first element in the array B, because the first element will always belong to the first array, first subarray. Okay, so this one we definitely cannot take. This one actually we can take if we just make an array like this. Like if we just make array like this, then definitely the second element would be in the array B. Okay. So if the second element was in the array B, then like it is always possible, right? My point is that suppose the second element was not 1. Okay. Let's just move to another test case for now. Let's say the second element was something else. Say this is 1, 3, 5, and 7. And k is equal to let's say 9. K is equal to 4. So actually what we can do is we want to make sure that the first element is not 1, right? So that what we can do is we can make one group as this one group as this one. So the first element would definitely be like 3. It would not be 1. So if the second element is not 1, then the answer is 1, because we want to minimize our answer, right? Now what if it is 1? Okay, so like in the above test case it is 1, right? I'll show you that. So in this test case the second element is 1, right? So what we can actually do, we'll try that. Okay, what if we try the third element? See, if we take the second element, then definitely the score is greater than 1, right? Like I am trying that my score is equal to 1. Like I'm trying to make my score equal to 1. And for that, I need that the first element is not equal to 1. If I put the first element equal to 1, then definitely the answer would not be 1. It would be greater than 1, right? So I'm trying my best to put the first element of B as not equal to 1. So, okay, we saw the case that if the second element is not equal to 1, then we can put. But it is equal to 1, right? So there is no point in putting this one into B. So if we don't want to put this one into B, then it has to be in the first subarray, right? Like we have to partition the array like this. That this is the first subarray, and then this one is the second. Like either this one or something else, like maybe ending somewhere else. But the first element in B would be this only, right? So actually we can take the third element as well. But here the third element, that is also 1. That is 1. So that is not of our purpose, right? So what if we try to take this one also into the first subarray? Then this fourth element would be 2 and our score would be 1. But the problem in this is we need to make 4 partitions, right? But if we give the first partition 3 elements, then we don't have enough elements. Like if we just, even if we give just 1 and 1 to the partition, then also we have only three partitions. So basically we actually cannot take 3 elements in the first partition. We can at max take only 2 elements in the first partition, and then we'd have to take 1 in each one, right? So that's the thing. We actually cannot take 3 elements in the first partition, and therefore the answer to this is not 1, right? We cannot make the answer as 1 because all of these 3 elements are 1. Like, okay, both of these are 1. Like this one doesn't matter. Maybe even if here it was 4 or something, then also the answer would not be 1 because these 2 elements are not 1. All right. So till here, is that clear? That why can't we make the answer as 1 in this case? Clear. Okay. So now, what if, like, okay, we just make with the fact that we cannot make the answer 1. But what if we try to make the answer 2? Like, can we make the answer 2? Let's see. Okay, so the answer 2 means that here, like at index I equal to 2, the element is not equal to 2. This A2 is not equal to 2, right? So basically, we were like content with the fact that we cannot make the answer 1, but now we are greedy and we want to make the answer 2. So how can we do that? Let's think. Okay. So here, if we just take, let's say we take the first element as this one. Okay, so this is not in the array. Then let's say we take the second element as this one. So this is in the array. And therefore the first element is not 1. I mean, sorry, it is 1. So the score is not 1. Now this one is not in the array. And if we take these two, then they are in the array. So actually, I have messed up. Okay. So we are trying to make the answer as 2, right? Okay, what we can actually do, just let me just think. Okay. Yeah, so we can do this. So we'll do this. 1, 1, 1, 2. Wait, how does? Yeah, so if we just do this, then the array B would be like what? Array B would be like 1, 1, and 2, and 0, right? So in this case, the second element is not equal to 2, right? So that's why we can make the score as 2 in this test case. Now, what if the array is like, what if n equal to k? In this sample test case, n is equal to k, right? So in that case, they are basically telling us to break this n length array into n segments. So that means that the segmentation is constant, right? Like we have to make it 1, 1, 2, 2, 3, 3, like, and so on. The segmentation is actually constant. Like we don't have any option. We have to put all the elements in different segments. So basically, we would have to take alternate elements into the array B. So in this case, the array B, what would it be? 1, 2, 3, 4, right? So the array is 1, 1, 2, 2, 3, 3, and 4, 4. So if we just segment it like this, because k equal to 8, that means that we have to break it like this only. We don't have any option. So if we do like this, then in the array B, this segment, this segment, this segment, this segment would go, right? So the array B would become 1, 2, 3, 4, and 0, right? So in this case, the answer is actually this index, because this ai equal to I, ai equal to I, equal to I, ai equal to I. But in this case, ai is not equal to I, the fifth element, that is not equal to I, right? So that's why the answer to this one is actually 5. Okay. Now, so we actually now saw the two test cases, this one and this one. These two we saw. So maybe we can have some idea, like maybe what if we think in general case? So let's think in general case. Okay. Let's say we have some n, we have some k, right? Now we have an array. We have an array a1, a2, a3, a4, a5, and a6, and let's say a7. For now, let's assume that k is equal to 6. Okay. So if k equal to 6, then what does that mean? That okay, suppose the second element is equal to not equal to 1. Okay, this is not equal to 1. Then what could we do? We can actually just take this as the first segment, and after that, whatever we do, the score will be equal to 1, or the cost will be equal to 1, because this will be the first element of the array B, right? And also we have enough elements to make 6 segments, right? Like basically, there are remaining 6 elements, and we have to make 5 segments out of that, because like one segment we made here. So out of these 6 elements, we have to make 5 segments, which is possible, right? So whatever we do, this would be the first element of the array B, and the cost would be 1, right? So if A2 is not equal to 1, then we are very happy that it is not equal to 1 and we can actually move on with our life. That and our cost will be equal to 1, the answer would be equal to 1. Okay, but what if now it is equal to 1, right? So what if it is equal to 1? Then what we can see is, what we can try is, what if this is not equal to 1? Okay, it's A3. Then we'll try that this is the first element. So if we want to make it the first element, then we would have to take these two elements as one subarray, right? So because we don't want to take these two elements. So in that case, A3 will become the first element. And it is possible to partition the array like this, because 5 elements are remaining and we want to make them into 5 segments. So it is definitely possible, like we can do this. So I just made 5 segments from 5 elements, right? So this is like, if A3 is not equal to 1, then this is the case. Like we can definitely make the answer as 1, right? But now what if A3 is also equal to 1? If A3 is equal to 1, then what do we do? You will say that, what if we try to take A4 as the first element? Then no, that is, you are wrong. Okay, why? Because if we try to take A4 as the first element, then what will happen is, we'll have to take this segment. But then the problem is that we have to make 5 segments out of these 4 elements. We have only 4 remaining elements and we would have to make 5 segments. So therefore, actually, we cannot take these 3 elements in the first place. Like, so it is not possible to take A4 as the first element of the array B. It is only possible to take either A2 or A3 as the first element of the array B. So if either two of these is not 1, then our answer is 1, right? So that's the case here. But what if they both are 1? What if they both are 1? Then what is the answer? So let's think about that, okay? So if they both are 1, then what we can actually do is, we can just greedily, what we can do? See, sorry. Yes, then answer is equal to 2. How? We can actually just make this partition and this partition. Like, since both of these are equal to 1, sorry, not this part, my bad. Yeah, this partition. So we take 1 in this and A2, A3 in the other one. So the array B will have 1 and 1 at the first 2 elements. So at second index, if you can see, the second index is not equal to 2. So the score is 2, right? Basically, we were not able to make score equal to 1, right? And we are able to make score equal to 2. So therefore, the answer is 2. The minimum score that we can obtain is 2. I'm sorry, like I'm saying score instead of cost, but I think you get the point. Just assume that I'm saying cost. So anyways, like if they both are 1, then we can actually do that. We can take them in same segment, right? And this is possible because here, like, we have already made 2 segments, this one and this one, and 4 elements are remaining. And like, we have to make 4 segments also. So it is definitely possible. So yes, if k is less than n, then answer is either 1 or 2. But actually, I haven't shown you the case where k is not equal to 6. Like, see, here I showed you that if n equal to 7 and k equal to 6, what would happen? But what if it is not the case? So we'll think about that as well, okay? So in this case, like, do you all get it? Like, what is the point? That if they are both equal to 1, then we can make the answer as 2. And if either one of them is not equal to 1, then the answer is 1, right? So does everyone follow up till here? Or do you have a doubt? Anyone, if you have a doubt, please feel free to ask. Please repeat this part. Which part? Like, till where do you understand? Did you understand that if either A2 or A3 is not equal to 1, then the answer is 1? You got that part, okay. Then basically, what if like if either A2 or A3 is not equal to 1, then answer is 1. So I am thinking about what is the answer otherwise. Okay, like if they both are 1, then what is the answer? So basically the array is of the form, the array is like A1, 1, 1. So these both of these are 1. And we have A3, A4, A5, A6, and A7. So in this case, actually, what we can just do is we can take this as one segment. So this will not be counted in the array. Then we can take this whole, these two ones as the other segment. And then we can just take like what we can just take all of these segments. So we made 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Wait. Oh, my bad. The numbering is messed up. This should be A4, right? A4, A5, A6, A7. A4, A5, A6, and A7. Yeah, so you got it, right? So we can just take these two elements and we will start with this. So this index is not equal to 2. Therefore, the answer is 2, right? So now I showed you the case that what if n minus k is equal to 1? Like basically this is the that is the case, right? That if n minus k is equal to 1, then actually you need to check the first two elements. I mean the A2 and A3 you need to check, right? But what if it is not equal to 1? Let's say k is equal to 4 and arrays of 7 length. Okay, so A1 we have A2, A3, A4, A5, A6, and A7. Okay, so we have this 7 length array. Now, guys, what if, so basically we cannot take the A1 obviously. What if this A2 is not equal to 1? Then we can take it, right? Because we can just do like this. So we can take A2 as the first element, so answer will be 1. If A2 is not equal to 1, then answer is 1. All right. But what if A2 is equal to 1? Then if A3 is not equal to 1, then also the answer is 1 because we can take these two elements, right? And we can always make like 4 segments, something like this maybe, right? We don't care about the rest of the elements because the first element is different from 1, right? So, right? But what if A3 is equal to 1 also? So at this point, A2 is equal to 1 and A3 is equal to 1. Then what if A4 is not equal to 1? Then we can take these 3 elements and A4, A5, and this whole segment, right? So if A4 is not equal to 1, then also answer is 1. So we can actually go till A5. Like if A5 is not equal to 1, then also we can, no, sorry, we can only go till A4. We can go till A4. Okay, so we can take A5 as well. So if A5 is not equal to 1, then we can take these 4 elements as the one segment, then A5 as the second segment, and these two. So we can go till A5 in this case. So if either like if till A5, if A5 is not equal to 1, then also the answer is equal to 1. But what if all of them are equal to 1? This is equal to 1, this is equal to 1. Then in that case also we just do the same thing. Like what we did above, we do the same thing. So we did like basically the array becomes A1, 1, 1, 1, 1, A6, and A7. So what we can do is we can just take this A1 and these two elements, and we just need to make 2 more segments, right? So we can just do like something like this, or maybe we can do something like this. Doesn't matter actually, like because the answer is 2. Because B would start with 1, 1 in that case, right? So that's the observation here, that if the certain starting elements are 1, then we cannot make the answer as 1. and the answer would be 2 in that case. And if either one of them is not 1, then we can basically take that as the first element in array B, and the answer would be equal to 1, right? So that is the point. And why can't we actually do this when n equal to k? Like I just told you that if n equal to k, then there is only one option. So this logic, where does it fail? Actually, it fails because we are taking these two elements, right? These two elements we are taking. And if n is equal to k, then actually we cannot take two elements in one segment because we have n elements and we need to make n segments also. So if we take two elements in one segment, then it is not possible. So we have, this is not, so that's why this logic fails if n equal to k. So if n equal to k, then we can just like make the array B. We can just make the array B and then check. All right. So yeah, we need to check the first few elements that are all of them one, and if they are not all one, then the answer is one. But what is the first few elements? Like, what do I mean with that? How many elements exactly? So let's calculate that. All right. So basically, we have an array of an n length. So right now I'll not use some 7 or something. Like I'll take generalized case. All right. So we have, this is one first element, second element, third element, up to nth element. All right. Then actually, what is the corner case? Like, what is the limiting case? Like, I want to figure out that till where can I take, right? So, let's say I take till some ith. Okay. I mean, if we are taking this as first array, then this element is the ith, let's say. Okay. Then till where can I be? Yeah, it can be till n minus k. Why? I'll just show you. Because let's say we have taken this 1, 2, 3 up to I minus 1 as first segment, right? So we need at least k minus 1 in this. Like I to n should have at least k minus 1 elements. Okay. So basically, um, just count that how many elements are there in between I to n. How many are there? It is just n minus I plus 1, right? And they should be equal to like k minus 1, right? So actually, we can take I up to n minus k plus 2. I mean, this is in one indexing, right? In one indexing, this is like this. So in zero indexing, actually, I will be up to, in zero indexing, I would be up to n minus k plus 1. All right. So this is the case. So basically, we just need to check that from I is equal to 1 to n minus k plus 1, we check that are all of them 1. And if all of them are 1, then the answer is 2. And if at least one of them is not 1, then the answer is 1. Okay. And this is the case where n is not equal to k. If n is equal to k, then we just make the array B and calculate the answer. So do you all get it, or does anyone have a doubt in this part? Clear? Other people, just repeat the last part. Last part means till where can we go? That part? N minus k part. Okay. All right. So basically, here I'll just take an example. Okay. We had A1, A2, A3, A4, A5, A6, and A7. And k is equal to, let's say, 4. Okay. So till where can we take? We can take till A5, right? Because we can make this A1 to A4 segment, this A5, A6, and A7. right? So we want to find that in general case, till where can we take? Okay, so let's say we have n elements. One, two, three, and this is something like this is I, okay, and this is n, or let's say this is I minus one, this is I. All right. So let's say I want to take this element right here. So is it possible to take it? Let's figure that out. Like, what is the condition that it is possible? Like, what is the condition that if I can take it? So basically, the condition is that we would make this first segment one segment, right? So this is the first segment, okay? And from the remaining elements, we need to make k minus one segments. So the remaining elements, how many are there? There are like from I to n. There are n minus I plus one remaining elements. And from them, we need to make k minus one segments. So in the corner case, like in the limiting case, what would it be like? It would be like every element in this is in different segment, right? So number of elements is equal to number of segments. So n minus I plus one equal to k minus one. So from here you get I is equal to n minus k plus two. And this is in zero index actually. Like this is zero index, right? I just took the arrays 1, 2, 3 up to n. So I is equal to n minus k plus 2 and like this is in one indexing. So in zero indexing, we can take till n minus k plus 1. All right. So is this part clear now? Whoever asked the doubt, is it clear now? Clear. Okay. Abhishek, I actually cannot look at codes right now because it will like waste others' time. So you can actually ask that in doubt section of TLE. Nitin was asking, when is answer 1 and when is answer 2? So answer is 1 when like up to I, like from 2 to I, all of the elements are 1, then the answer is 2. Because definitely one of the elements will be 1. And if either one of these elements are not equal to 1, then we can take that as the first element. So the answer would be 1. I mean, I just talked about that for last 20 minutes. So you can actually look at the YouTube video if you are not getting it right. Abhishek, you can like you can just ask him doubts. Like maybe even if I look at the code, maybe I will not be able to spot the bug or something. So I can't waste time on this. So yeah, I'll show you the code also, although it is not very tough to implement this thing. Utkarsh, we are only checking for 1 and 2 because I just proved that the answer can be only 1 or 2. Like uh, during this whole explanation, I just told you that if all of let's say k equal to 4 and n equal to 7, then if all of these three are equal to 1, then or let's say all of these 4 are equal to 1, then the answer cannot be 1. But in that case, we can make the answer as 2 because we can just take this a1 and this a2 a3 as a segment. So the answer will be 2. And if one of them is not equal to 1, let's say a4 is not equal to 1, then we can just take the segment as a1 to a3 and then a4. Okay, so that's why the answer will be either only 1 or 2. Answer, how can it be 3? Like, why 3? Like, if it is not 1, then I just showed you that how to make 2, right? Like, if it is not 1. If it is not 1, that means that all of these are 1, right? If the answer is not 1, then that means that all of these elements are equal to 1. So in that case, you will just take A1 as the first subarray and these two as the second subarray. I think most of you have understood. So yeah, I'll show my code. Like if someone still has a doubt, then they can ask in the doubt section. Okay. So yeah, this is my code. I just took the input of array A, like nk, c and nk, input the array. If n is equal to k, then I just made the array B, right? So for I equal to 1, I less than n, I plus equals to 2. So like alternate elements of A, I am putting into B. All right. So this is the array B. I have made the array B. Actually, the last element is not 0. I did not do that. Okay. And then I just made a loop of n by 2. Like I equal to 0, I less than n by 2, I plus plus. So if vi is not equal to I plus 1, because 0 indexing, right? 0, 1 indexing. So if vi is not equal to I plus 1, then just print the index. That is the cost. And see out n by 2 plus 1. Like if this while loop, this for loop doesn't break, like it doesn't return, then that means that all the elements are equal to I plus 1. So the answer would be just length of B plus 1. Like the last element, which is 0, right? So that's why the answer would be that. And otherwise, like this was for n equal to k. And if n is not equal to k, then I just counted the number of ones from 1, like from index 1 to n plus k plus 1, n minus k plus 1. I mean. Like actually this is 0 index. Like the count function takes the begin and end iterator. So the end iterator actually not inclusive. So this whole thing counts the number of ones from the index 1 to the index n minus k plus 1. And if that is equal to n minus k plus 1, then that means all of the elements are 1, right? So I just printed 2. And otherwise I printed 1 because one of the elements is not equal to 1. So I'll just take it as 1. Nitin, you are asking that how is the answer 5 for this array. So if you can observe, n is equal to k in this case. So basically you have to break 8 elements into 8 subarrays. So isn't that pretty fixed? Like 1, 1, 2, 2, 3, 3, 4, 4. So don't you have to break all of the elements into different ones? Because n is equal to 8 and k is also equal to 8. So you have to break 8 subarrays. So therefore you have to make this one only, right? You have no choice. Yes, answer is only possible if n equal to k. Answer greater than 2 only possible if n equal to k. If n is not equal to k, then answer will be either 1 or 2. That's what I proved. Okay. So let's move on to the problem number C. This is customer service. Okay. Actually, honestly I think that C is easier than B, but maybe that's just me. I mean, one doubt. Abhishek is having a doubt. What's the doubt? I don't really know the context for this code, like what is V and all. So please don't send codes in the chat. Okay. Like, there is a facility available to you which is called doubt support. So please ask him that thing. Okay. All right. So the problem C. Problem C says that Naika started working as a queue manager at the company Black Contour. He needs to choose the order of serving customers. There are total n queues, each initially containing 0 people. In each one of the n moments of the time, there are two sequential events. Like there are n moments of time and there will happen two events. New customers arrive in all queues. More formally, at the jth moment of time, the number of people in the ith queue increases by a value of aij, a positive integer. Nika chooses exactly one of the n queues to be served at that moment in time. The number of customers in this queue becomes 0. So when Nika chooses to serve the queue, the number of customers becomes 0 in that queue. And at each moment in time, queue will, like, some elements will be added to the queue. Okay. Let the number of people in the ith queue after all the events be xi. Nika wants the max of the collection x1 to xn to be as large as possible. Help him determine the maximum value he can achieve with an optimal order of servicing the queues. Okay, so we want to maximize the max of something. So let's look at the problem. Okay, so the problem actually says that there are n queues. Okay. So let's say n equal to 5. Then actually there are n queues, right? So let's say currently there are 5 queues and some customers are there in a queue. Now we have been given a matrix like Aij denotes that at the jth moment in the ith row, Aij customers will appear. So let's take the fourth sample test case. So this is row 1, this is row 2, this is row 3, and this is row 4, right? So initially they are all zeros. Okay. So this is of n equal to 4, right? So they're all zeros. Now, initially, at the first moment, 4 will come like in the first row, 1 will come in second row, 5 will come in third row, and 1 will come in the fourth row, in fourth queue, right? So 4151 it will become. Okay. 4151 it will become. Now, we have to choose any queue to clear. Like we can choose any element and we can make it 0. So let's say we choose this 4 or the index 1, right? So it will become 0. Now at the next moment, 2 customers appear in line 1, third 9 appear in line 2, 5 appear in line 3, 2 appear in line 4. So 2952, we just add. So it would become like 2, 9, 5. Okay, so actually 9 is added. So 2, 10, 10, and another 2 is added. So this 1 becomes actually 3. Okay. So that's how, and yeah, and then after that, we'll choose a queue to service. So let's say we service this queue. So it would become 0. So it would become 2, 10, 0, and 3. Then again, this happens actually 4 times. So this one, like this thing happens, another event, and again, this last event happens. So basically, after the end, like after the end of last event, whatever the array is remaining, some array will remain, like the number of people. So you need to maximize the max of that array. Max. And max is basically the first non-negative integer which is not in the array. So I think that you already know that. Like, for example, the max of 2 to 1 is 0 because 0 is not there in the array. Max of 3101 is 2 because 0 and 1 are in the array but 2 is not in the array. And max of 0312 is 4 because 0, 1, 2 and 3 are in the array but 4 is not in the array. So that's what the max is. So we have to maximize the max. Okay. So what I actually did I thought about what will happen, like the final array, how will it look like? Okay. So let's say we have an input matrix. So I just copy these samples. 4 to 270, or maybe I can paste it somehow. I'll try that. Okay, I cannot paste it. Never mind. 4 to 70. 1 9 3 1 5 5 5 and 1 11. 1 to 1 more. Okay. So this is actually the matrix that is in the input. So this row 1 is for the Q1, like the first Q, that how many customers appear after each second. So actually, let's say the final error actually depends on what operations we do, right? The final error depends on what operations we do. But so let's say I just do all the 4 on this one. Like I am very biased and I do all the operations on this array. Like we need to do 4, we need to do it 4 times, right? After the first second, after second, third second, fourth second. So let's say I just do all the 4 operations in this one, right? So what would happen in that case? Like how will the final array look like? In the final array, this would have 0, right? Because after the 4th second, I serviced the people from this queue, so it became 0. In this one, it was the sum of this, right? The sum of these 4 elements, because I did not service them, so they just kept coming. So 1 9 10 13 1 14. Okay. Then we have like some of these, so 15 11 26, and this is 5. So the final array is this in this case. So what is the answer? The answer is 1. Like the max of this array is 1. Like I'm not saying that this is the optimal case. Like doing all the 4 operations on this one, I am this is not optimal. But if we do that, then the max would come out as 1. Okay. Because 0 is there in the array, but 1 is not there in the array. So max is 1. Right? But so what you can actually observe is that the customers keep coming. Okay. So actually, what I want to say is that look at this queue. Okay. Let's say look at this queue. So if you look at this queue, um, let's say 9 people came after t equal to 2, 9 people came, right? And you service them. You service this queue at that point. All right. And you did not service this queue till the end again. So 3 and 1 are still remaining. So if you service this queue at this point, then 3 and 1 are still remaining. So so finally 4 people would remain, right? And similarly for this one, if you service this queue at this time and you service this queue at another, like once more at this time, then 17 people would remain here, right? So we have serviced like at t equal to 1 this queue, t equal to this queue, sorry, t equal to this queue, t equal to 3 this queue, and after t equal to 4, let's say you service this queue, like, right? So this will become 0, and you did not service this queue at all. So therefore, the answer is just 5. Okay. So actually, this is a great way to visualize the problem, right? That basically you can service some queues, and that I'm drawing as bars, like these bars or these partitions are there, and the last partition, like let's say in this row, the last partition is here. So I serviced all the customers up till here, right? So anyone coming after that, they will remain. So 17 will be the answer. Like 17 will be the final number of customers in the queue. Okay. So like in general, if I say I have to put some bars and I have to maximize the max. Okay. So I have a, let's say, matrix. or let's just take this one only. Or yeah, let's just take this one without all of these drawings. Yeah, so this is the input that we have been given. Now we want to maximize the max, right? Maximizing the max, what does that mean? That means that, let's say, so basically there should be a zero in the array, right? There has to be a zero in the array. Like if there is not a zero in the array, then the max would be zero, right? So therefore we first try that there is a zero in the array. Okay. So therefore we service one of the rows. Like basically actually we whenever whatever row we service in the end, that would have a zero, right? So this has a zero. So therefore max cannot be actually zero. Max has to be at least one. Like the max will be at least one. Okay. Because the row that we service at the end, that will have zero customers. So we have a zero in the array. Therefore max is not equal to zero. So let's say we service this row at the end. So there is a zero here. Now we need to increase the max even further. So we need a one as well. Okay. We need a one. So how will we get a one? We can get a one by just servicing this row at this time. Right? So this will give one. Then we need a two also. We need a two also. So how we get a two? We can get a two by just doing something like this. Like we put a bar here. Or let me make the bar more in a different color. So one bar we are putting here. Another bar, sorry, not here. Here. Okay. Another bar we are putting here. So this is zero, this is one, and this is two. All right. So this will give us two. And the third bar, like in this column, we have to put somewhere, right? So let's say we put it anywhere. Let's say we put it here. Then this would have how much? 21, right? So the max is 3. The max is 3, right? So that's how you can make the max as 3 by putting the bars like this. Or maybe you put the bar something else. Like maybe you put this last bar as here. Then in that case also, this would be something else. This would be 4 plus 2, 6 plus 2, 10 plus 27. But in either case, the max is 3. The max can change only if you can make a 3, right? But you cannot actually make a 3. See, 0, 1, and 2, we have already gotten. So the max is 3 right now. So if we can get a 3 also, then the max would increase. It would become 4. But actually, we cannot get a max of 3 from this row, right? So therefore, the answer is 3. So basically, what you can actually observe is that we have to make certain elements. Like we have to make 0 as well. We need to make 1, we need to make 2, we need to make 3. And whenever we fail to make any element, then we are done. Like this element will be the answer then. Let's say we can make 0, 1, 2, 3, but we cannot make 4. Then the answer would be 4. And how we are making it, we are basically taking some certain last elements of a row, right? Let me just explain that from that example only, that we are taking certain last elements. Yeah, so let's say this is the input. So from each row, we can take the last certain elements. Like either we can take 0, or we can take 1, or we can take 2, or we can take 3 from each of the rows. So let's say we take the last one element from this. We take the last two elements from this. Actually, we don't. We take the last two elements from this one. We take last 3 from this one. and we take none from this. So basically the partition is here. So in this case, the answer would be like the array would become 0, 1, 21, and 2. So therefore the max is 3. Okay. So basically what we have to do is we have to take certain last elements from the array, right? And we can do that, and we'll try to make the max as large as possible. So in this case, we first we try to make 0. So we'll make 0, let's say by choosing like this row as the last. Now we want to make a 1, right? But the thing is that we cannot make a partition here. See, the thing is that the partitions have to be unique. Like basically, you cannot take you cannot put two partitions in the same row. Like this, we cannot do. This is not allowed. So basically, you have to put the partitions in different rows. I mean, in different columns, right? So if one is here, then the other one has to be here. Other one has to be here. Okay. So let's say you try to make 0. So 0 actually you can only make if you in that 0 will be only in that row where you put the partition in the end, right? So this will be 0. Then if you put the partition, like okay, now you need 1, right? So how can you get a 1? Let's say you put a partition somewhere here, like you take two elements. Either like see if you put it here, then you will take these two elements. So if you put it somewhere here, you will definitely take two elements. But if you're taking two elements, then definitely the max cannot the sum cannot be 1, right? The sum of two positive elements cannot be 1, right? So therefore you have to take like only the last element. Like basically you have to put a partition either here, like either of these three places, or maybe you can put it here also, but that won't do it. Like that won't give you 1. So actually you have to put it either here, here, or here. So if you put it either here or here, then you will get a 1. But if you put it here, then you will get an 11. And then you cannot get a 1 in the future, because then you would have at least two elements, right? So therefore you have to put it either at this place or at this place. So let's say I put it at this place. Now you have a 1 also. Now you wanted 2. But you cannot put the partition at 0 or at 1. Like you cannot put the partition. Basically, you cannot take the last 0 numbers or last 1 numbers. You have to take at least 2 numbers to make sum as 2. So that means that they have to be equal to 1 and 1, right? You can only take two ones to make the sum as 2. So 1 and 1 you have to take. Like the partition will be here. So as you can see that only the last ones we have to take. Like basically, let's say we want to make 1, then we can only do it using this last one. We have to make 2. See, let's say we have to make a 2, all right? But let's say 2 was here. Now some of you might say that we don't need to take two ones. We can just take this 2 like this. But actually this is not allowed. Like this is allowed, but we won't do this because we need to take a 1 also. If we took a 1, that means that already there's a partition here in this column. In this column, there's a partition already. So actually we cannot make a partition here. So definitely we need two ones. Okay, so therefore we need only the ones count. Only the trailing ones matter. Like, do you both get it? Yeah, so therefore only the last ones. Like in this row, there are zero ones, like the trailing ones. In this row, there's only one trailing one. In this row, there are 0 trailing ones, and in this row, there are 2 trailing ones. So basically, from this row, we can take a 0. From this row, we can take a 1. From this row, we can take a 2. And from this row, we cannot take 3. Like we cannot make 3, and we cannot take 3. Right? So we can only make 0, 1, 2. So the answer is 3. Right? So if I just show it for other test cases, in this case we have 1, 2, and 2, 1. So the first row, in the first row there are 0, and second row there are 1. So 0, let's say, I just copy it, 1, 2, and 2, 1. So in the first row we have 0, and second row we have 1. So from here you can get 0, from here you can get 1. So therefore the answer is 2. Then let's say we have something like 2, 2, 2, 1, 1, 1, and 1, 1, 1. So here we have 0, here we have 3, and here we have 3. So first of all we need 0, so we'll pick it up from here. Then we need a 1. So actually we can just get it from this 3. Like we can only take this 1. So we can get a 1 from here. And we can get a 2 from this one. Right? But actually the strategy applies here as well. Let's start. You need an optimal strategy also. See, I'll give an example. So let's say we have one row which has 0. We have one row which has 2. And we have one row which has 1. Okay. So now if you take 0 from 0, okay. Now if you take 1 from this 2, right? But now you cannot take 2 ones from this one because there's only 1 1 right now. So actually the order matters. Like you cannot just arbitrarily take. You have to take 1 from this one and 2 from this one. So the max would be 3. So what you actually do is you can just sort the array. Like you can make this array of 0, 2, and 1, and you can sort it. You can sort it and just find the next element which is just greater than what you want. So let's say our array is like 0, 1, 3, 4, 7, and 7, and 7, and 7. Okay. So basically, first we want a 0, right? So, okay, I sorted this thing, so it is sorted. Now we need a 0. So 0 will get from this. Then we need a 1, right? So 1 will get from this. Then we need a 2. So 2 will get from this. And we need a 3. 3 will get from this. And let's say we have something like, just a minute, 4, 4, 4, and we have, let's say, 10. Okay. So now what we need is a 4. So we'll get a 4 from here. Now we need a 5. But we cannot get 5 from here, right? We cannot get 5 from here as well. So we'll take a 5 from here. Right? So therefore the answer to this would be 6. So that's what you will do. Like you can just apply 2 point, like you can just make a pointer and iterate it from left to right. Or maybe you can apply lower bound and find the first element which is greater than or equal to your thing. Okay. So that's what you will do. You will just make the number of 1 arrays and sort it, and then just use 2 pointers or lower bound to find the answer. Okay. So that is the logic for this question. So do you all get it? Okay. So I'll show you the code for the sake of it. All right. So all right. So we have this like I took the input vector of vector I for I equal to 1, I equal to 0, I less than I plus for j equal to 0. I took the input c in ij. So I took all the elements of row I in this for loop. Then I made, and yeah, this array is like the number of ones array. Okay. And using this code, I just counted the number of arrays. Like while vi dot size, while vi dot size is not equal to 0 and vi dot back is equal to 1, then I just array dot back plus plus. So I increase the count and I pop back vi. Okay. Then I sorted this. So basically, this is the array for the number of ones. And then I sorted this array. And now I have a counter, which just tells me that, okay, which number do I need next? So first of all, I need 0, then I need 1, then I need 2, etc. Right? And this I pointer is that till where have I taken? Okay, so I is lower bound, ARR begin plus ARR end, like countless. So basically, I am just searching for count plus 1. Yeah, count plus 1 I'm doing because 0 will definitely be there. It is definitely possible to make a 0, right? So therefore, I am starting with 1. So count plus 1 I am doing minus ARR dot begin. All right. So I'm starting with ARR dot begin plus I because I actually cannot take those. Like, see that actually I made a wrong summation because I was starting from ARR dot begin only. So that is wrong because see, let's say you have an array on 0, 3, and 4. So first of all, you will take 0 from this one. So my algorithm, what will it do? It will take 0 from this one. Then it will search for something greater than 1. So it will take 1. Then it will take 2 from this 3. Then it will take 3 from this 3. Then it will take 4 from this 3. So that is wrong, right? Because it is taking this 3 multiple times. It is choosing this 3 multiple times. Therefore, it is wrong. And to handle that, I just made a pointer called I. And I just did I equal to lower bound ARR begin plus ARR end. And I just search for count plus 1. Like the first element greater than equal to count plus 1. And if I equal to n, that means that I is equal to end iterator. Then basically it did not find any element greater than equal to I. So I just printed count plus 1. And I took the minimum with n because max cannot be greater than n, right? And I don't think this is very necessary because count plus 1 will be like when it searches for n. Okay, actually it is necessary. So suppose let's say the array is like 1, 2, 3, 4. Like n is equal to 4. Okay. Then what will it do? It will do something like search for 1, right? So it searches for 1 and it finds a 1. So it will take a 1 from here. Okay. Then it will take a 2 from here. It will take a 3 from here. And then it will take a 4 from here. But this is wrong because we need a 0 as well. So actually, if we are able to take all of the elements, then that means that see if we are able to do this, then that means that we actually need to make the last element as 0. We need to take 0 from here. We need to take 0 from here. And so the answer will be 4. That's why I did minimum with n comma count plus 1. Actually, if you just did count here, and count here, then also it would be fine. Then you wouldn't have to take minimum. So actually this code is not very clean. I'll share a cleaner code in the YouTube description, okay? So if I is equal to n, then that means that it did not find any number greater than equal to count plus 1. So we cannot make count plus 1, so I printed count plus 1. And I returned. And otherwise, I just increase count plus and I plus. So basically, I have taken till I. So I increment the I that I can take from here next. And then I just printed like count plus 1 comma n minimum. I took the minimum with n because of this reason. And if the array is like 1, 2, 3, 4, then my algorithm will say that okay, take 1, take 2, take 3, take 4. And the answer is 5. But that is not true because we need to take 0 from this. So I took the minimum with count plus 1. Okay. So I hope it is clear. If it is clear, then I'll just move on to the next problem, that is D. Graph and graph. So there are two graphs. You are given two connected unrelated graphs with the same number of vertices. Okay. In both graphs, there is a token located at some vertex. All right. In the first graph, the token is initially at vertex S1. And in second graph, the token is initially at vertex S2. All right. the following operation is repeated infinite number of times. Okay, so there are two tokens, there are two graphs. On graph 1, it is at S1, on graph 2, it is at S2. The following operation is repeated infinite number of times. Let the token currently be at vertex V1 in the first graph and at vertex V2 in the second graph. So the two tokens are at vertex V1 and V2. Now vertex U1 is chosen adjacent to V1. Vertex U2 is chosen adjacent to V2. The tokens are moved to the chosen vertices. Like in the first graph, the token moves from V1 to U1, and the second graph from V2 to U2. And to do this, the cost is equal to mod of U1 minus U2. So basically, um, if currently they are at some vertices, then they'll move to some adjacent vertex, and that cost will be equal to U1 minus U2, come mod. Okay. So determine the minimum possible total cost of all operations, or report that this value will be infinitely large. Okay, so this means that, see, this operation is repeated infinite number of times, right? That we take, like, basically, there's a graph. There are two graphs. Let's say this is one graph, this is another graph. Okay, both have four vertices. Both have same number of vertices. Okay. Now I'll just number them 1, 2, 3, 4, and 1, 2, 3, and 4. So let's say currently the tokens are at 1 and this one is at 4. So now if I move this token to 2 and this token moves to 1. So basically it can move to any adjacent. So this token can actually move to either 3 or 2. Okay. So let's say this happens, that this token moves to 2 and this token moves to 1. Then the cost of that operation would be 1. Like the mod of 2 minus 1. Mod of 2 minus 1. This is the cost of this operation. And basically what you have to do is that you have to do this operation infinite number of times. Right? And you have to find the minimum total cost in doing that. Okay. So the first thing that you might ask is that how can infinite number operation be, like, how can the cost be finite? Like, if you are doing it infinite times, then how is the cost not infinite? So why is the cost not infinite? You might wonder that, right? So the answer to that is, if the cost is 0, like, basically you just do some operations in the starting stage. So suppose the first operation costed 2. The first one costed 2, second one costed 3, and so on. Like, third one costed 1 or something. Then let's say this costed 0, this costed 0, this costed 0, this costed 0, this costed. So if they are continuously costing 0, then that means that this infinite series ka sum, it would be finite. Like, this sum is 6, right? So basically you need to find a stable state. Like, a stable state is that the cost is 0 after all the steps. Like, basically, let's say in this graph, you have, let's say the pointers were something like, not like this. Okay. Initially, the tokens were something else. They were, let's say this one was at 4. Okay. This one also at 4. So when you move to this 2 and 1, so the first cost would be like what? So yeah, 1. Correct. So here you move to 2 and here you move to 1. So the cost is equal to 1. Now what you do? Let's say you do that. Okay, you go to this 3. And here you go to this 2. Okay. So again the cost is 1. So right now the pointers are like at 3 and at 2. At 3 and at 2. So the cost is 1. Now what? Now let's say this pointer goes to this 1. Okay. So this one goes to the 1 and this pointer also goes to the 1. All right. So what's the cost in this case? It is just zero, right? Because one and one are same. This is zero. And now what actually you can do is, yeah. So what actually you can do is just go to two. So this will go to two. So the cost is zero. Now both are at two. Now they can both come to one. So the cost will be zero. So and so on. So the answer to this would be two. That's why for an infinite series, the cost can be finite. Yes. So basically, finally, what will happen is that there will be some edge. Like there is some edge which is same. Like this edge 1, 2, and this edge 1, 2, they are same, right? So therefore, if both the vertices, like if both the coins end up there, then it is a stable state. And the answer is not infinite. But if they cannot end up at that edge, then the answer is actually finite. Okay. So if there is no common edge, then the answer is infinite. But it can happen that there is a common edge, but the answer is still infinite. That can also happen actually. How? Because they're not able to reach at the same time. Let's say this is graph one common. This is one graph. This is one, and another graph is this. So the graph is same. And but in second graph, it starts from here. So in the next move, it will go to two. This will go to one. The cost is one. And again it will come back to 1, it will come back to 2. So the cost is 1. So even though there is one common edge, this is common 2 and this is also one common 2, but still the answer is infinite because they are not able to reach the same vertex at the same time. Okay, this is one thing. So now, like the question is this actually, like, till right now, what I have explained is the question. Okay, now how do I solve it? Let's think about that. Okay, I'll talk about that. So first of all, I talked about, like, first of all, I thought that this cost is actually very, like, weird. It's very arbitrary. Like there are two graphs like this. Let's say this whole thing is graph one. This is graph two, and there is some numbering of vertices. What is the number? So like the graph is like this, and the vertices are numbered. And here the same number of vertices are there. Here there are six. There are six here also, right? This is the graph, and the numbering of them is something. So this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So some numbering might be there. And the cost is the difference of that numbers. But the numbers are arbitrary, right? Like the numbers don't make any physical sense. Like we can put the numbers at anything. So they don't have any physical sense as such. So the numbers, so therefore this cost thing is actually very arbitrary. They are random, yes. So we cannot actually use that fact. Like we actually cannot use this fact that this is equal to u1 minus u2 and think about something because this is completely arbitrary. It can be anything, right? So what I actually observed is that this thing cannot be used, right? So I thought, okay, I cannot make a strategy. Like I cannot make a greedy strategy because the numbering is just arbitrary. So what if I try to do DP? Okay, so actually, um, basically what our aim is that our aim is to make both the vertices reach the same, both the coins reach the same vertex, and also that will have an edge. Like basically, all the common edges in these two graphs. Let's say this is one, this is two, and this is one, this is two. So this 1, 2 edge, 1, 2 edge here, and this 1, 2 edge here, they are common, right? So we want to try to bring this token to either one or two, like both of these token to either one or both to either two, right? And we need to find the minimum cost in doing that. Correct? Yes, they need to need the same edge in the both graphs, but in the same node also. Like not the same edge, but the same node. So it like cannot happen that this is 1 and this is just 2. Like this is not allowed. Basically, we need to try that they both reach the same node and that node has a common edge, right? So so basically, if we can find such a edge and we can find the minimum cost to go there, like in the starting there somewhere else, right? So we need to send them there, and that will have some cost. So if we can find that cost, then we can actually say that is the answer. I mean, over all the common edges, like this is 1, comma 2. This 1, 2 is common. 1 to 2 is common. Then let's say this is 3, this is 4. And let's say this is, okay, no, wait, 2, comma 3. Oh, this is 2, comma 3. This is 2, comma 3 edge. And this is 3. So let's say this is 2, comma 3 edge. So now in these two graphs, two edges are common. This is 1, comma 2 edge is common. And 2, comma 3 edge is common. So if I just make both of them reach either 1, 2, or 3, like both of them either reach 1, 2, or 3 at the same time, then definitely like the minimum cost of them, that would be my answer. Like the cost of reaching either 1 or 2 or 3, that is my answer. So I'll just check out all the vertices which are having a common edge between these two graphs. I'll check all of them, and the minimum of that is the answer, right? And if you cannot reach these vertices at the same time, then the answer is infinity, because even though there's a common edge, but you cannot reach that edge at the same time. So the answer is infinity. So what I just want to do is find the minimum cost in reaching the vertex I in this one and I in this one also, right? Yes. So you need to find the cost to reach certain nodes. To reach I in this one and also say it's the same node I in this one. So how do we find that? That is the problem now. Like how do we find that? Okay. So for that I just kept a DP. Like I just kept a DP of IJ. So DP IJ, that is like the minimum cost to reach node I in graph 1, and similarly node J in graph 2. Okay. So this is my DP. Like I am just storing the minimum cost to reach both of these vertices. So if I have this DP, then I can just iterate over all the i's. Like I'll just iterate over DP I comma I, such that I has a common edge. Like if I has a common edge in the both the graphs, then I just iterate over all of these i's, and the minimum value of DP is the answer. And if all of these are infinity, then that means that we cannot reach them. Like we cannot reach this I comma I state. So therefore the answer would be just infinity, right? So that I'll try to calculate this DP I comma j, that what is the minimum cost to reach I comma j from the starting vertices. So definitely what is the base case? Base case is like they start from S1, right? So the DP of S1 comma S2, that would just be 0, right? You don't need to make any cost, because the cost is actually positive. The cost is equal to mod of u1 minus u2. So if you make a move, it cannot happen that you are negative, you are having negative cost. The cost is non-negative. So therefore, the DP of S1 comma S2 is just 0. So this is the base case. But what if I want to calculate the DP for IJ? DP for IJ, how do we calculate? So DPIJ is the minimum cost to reach I comma j, right? So if we are reaching I, right? If we are reaching I, then that means that we had, like we were at some vertex X in the first graph. Like in the first graph, we were at vertex X, and then we went to vertex I, right? And in the graph 2, like and X and I have an edge. X and I have an edge, right? And in graph 2, we were at vertex Y, and we went to vertex J. So therefore, Y and J have an X. right? So the cost would just be the minimum cost to reach xy plus absolute value of the final destination, so I minus j, right? So dpij is equal to this, like whatever x and y are adjacent to this I and j, we can just reach from xy to ij if there's an edge from x to I and y to j. So this is our transition, like that what is dpij. But actually we need the minimum value, right? We need the minimum value of this cost, right? So how do we do that? We have to like iterate over all the neighbors of I and j, and we have to basically like take the minimum of xy. But the thing is that this is not a tree. Like it's a graph, right? It has cycles. So it is not that simple actually, because in what order do you make the DP, right? So actually this is the starting point only. That dpij equals to dp of xy plus mod of I minus j. So where xy, like there's an edge between I and x, and there's an edge between j and y, right? So this actually should remind you of something. Like basically you want to reach this node ij, and the cost to reach this node is basically cost to reach xy plus mod of I minus j. So isn't it like a graph or something? Like let's say we have a 2D DP, right? We have a 2D DP, but dpij. So if we just think of it as a graph, where each node is a particular value of ij. Let's say I'll take an example. N equal to 3. Okay. So we have 1, 2, and 3 in both the graphs, right? So now, how many DP are there? Like there are 9 DP states. DP 1 से लेके 3, and in J also 1 से लेके 3. So there are 9 DP states. So if you think of it as a graph with 9 nodes, then you can do that, right? So basically, this node 1 is 1 comma 1. Node 2 is 1 comma 2. Node 3 is 1 comma 3. This node is 2 comma 1, 2 comma 2, and 2 comma 3. And this node is 3 comma 1, 3 comma 2, and 3 comma 3. So basically, these are nodes. Like actually, DP is just a graph. I mean, if you know that fact, that DP is just DAG, dirty diagonal graph, then actually this problem becomes quite easier. Basically, what you can do is you can represent this as a graph. Okay. So DP 1 to 3 and DP 1 to 3, we have 9 states. So I just drew them. Now see, just think about from 1 1, where can you go? You can go wherever, like you can go from 1 1 to xy. If in G1 there's an edge from 1 to x, and in G2 there's an edge from 1 to y, right? So basically, I'll just take an example. I'll just make a graph. I'll just make 2 graphs of 3 nodes. Okay. So let me do that. So let's say we have one graph of 3 nodes, 1, 2, and 3. Edge here and an edge here. Okay. And another graph we have on 1, 2, and 3. So we have an edge here. Let's say 1, 3 and 2, 3. Okay. And let's say 1, 2 also. Okay. Or not 1, 2, that will make this very dirty. Anyways, so from 1, 1, just think about where can we go. Like either see from 1, we can go to 3 in the first graph. So basically we can go to all of these 3 nodes. But if on see from 1 1, where can we go? Just think about that. So in graph 1, we can go to either 3 or 2. And in graph 2, either we can go to 3. Okay, we can only go to 3. So from 1, 1, it is possible to go to 3, 1. Uh, sorry, no, yeah, 3, 1. I'm sorry, 3, 3. 3, 3 and 2, 3. Yes. So this is one edge. Now from 1 to, it is possible to go where? It is possible, like from 1 to, it is possible to go to 3, 3 or like um 2, 3. So from 1 to, it is possible to go to 3, 3 or 2, 3. So 1, 2, 2, 2, 3, right? So like that's my point, that you can actually make it like a graph containing n square vertices. And basically these edges also have weights. See, what we want, like why do I make it as a graph? I'll explain now. Because this dpij is just dpxy plus mod of I minus j. That means that basically, let's say the S1, that the starting node of graph 1 is 1, and starting node of graph 2 is equal to 3. So therefore, it starts at 1, comma 3. So basically, distance of this node is 0. Like the cost for this node is 0 actually. Now what you can do is basically from all of, like from this node, from where can you go? From this node, where can you go? So you can think about it. So 1, comma 3, so you can go to like 1, say you can go to 3 or 2, and from 3 you can go to 2, right? So in total you can actually go to either 3, comma 2 or 2, comma 2. So either I'll actually remove these edges right now for now. So from 1, comma 3 actually you can go to 3, 2 or 2, 2, right? So either to 3, 2 or to 2, 2. Now this had weight 0. I mean this had cost 0. If you want to move to 3, 2, then it would have cost 1, right? So basically you can add the, like you can make this edge weight as 1. So if you are traversing this edge, then this cost 1 would added. So here to reach here the cost is 1, and this cost is actually 0, because 2 minus 2 0. So this edge has weight 0. So actually you can make this graph and you can apply Dijkstra on it. Like what you want to just do is you are starting from this 1, comma 3 node, right? Sorry, you are starting from this 1, comma 3 node. Here the distance is 0, and you need to figure out the cost to reach all of these nodes, like this node and this node, right? Basically that's what we are doing, right? That we want to figure out the cost to reach same node, and the minimum of that cost would be our answer, right? So suppose if I am able to reach 1, 1 from 1, 3, actually that is not possible, because that would need an edge from 1 to 1, which is not possible. But let's say I am able to reach 1, 2, 2 from 1, 3. So that means the cost of this 2, comma 2, like the edge weight is 0. So I can reach here in 0 cost. So um the cost for this node, like the DP for this, is 0. So actually you can apply Dijkstra here, because this dpij equal to dpxy, like we are coming to ij from xy and adding something. So this is the edge weight, mod of I minus j. And since this is positive, right? This is always positive. Therefore, you can apply Dijkstra here. That you start from this starting node 1, comma 3, and just apply Dijkstra to find all of the shortest paths. Like it will find all shortest paths, but you only need these I equal to j ones, right? And out of all of those, you will check the minimum one. Like the minimum cost you will check, and that would be your answer. So is it clear? Yes. So yeah, you just do that. So it will, okay, actually, there is one good question that why would this pass in, like, why wouldn't this give TLE? Because there are n square nodes, right? But okay, n square passes. So the number of nodes is not a penalty. So n square is actually passing, right? But what about the number of edges? So TC of Dijkstra, what is it? Like Dijkstra, it is like I think O of V plus E log E or something like that. So if this E is very large, then it will give TLE. So like this V is n square, right? V is just n square. But what is this E? E is actually m square. Like, see why? Because basically in this graph, edges between, like, see, what is the number of edges? We need to count that, right? So that would just be like, let's say we need to count the number of edges from 1. Okay. So from 1, where can we go? So let's say 1 has degree as D, like it has D edges. So we can go to D, or let's say 1 comma 1, I mean. So in graph 1, vertex 1 has D1, and in graph 2, vertex 1 has D2. So from 1 comma 1 till where can we go? Like how many nodes are there where we can go? So that's just D1 into D2, D1 times D2, right? From 1 1, we can go to D1 to D2 nodes because there are these many edges outgoing. So we can choose anyone from here and anyone from here. So from 1 1, we can do like this. So from every node, we can go di into, I mean, di1. Like if we are at node I comma j, like I in the first graph and j in second graph, then it is just like di comma 1 into d j comma 2. Yes. So that is the number of edges outgoing from a certain node, like from I comma j. This is the number of edges outgoing. And if you just take the summation, that will give the number of edges that will give. So if we take summation over all ij, I equal to 1 se n and j equal to 1 se n. So this is the number of edges. And that is actually equal to, like, if you can just see that you can just take this j out of the summation. So if you do this one, like j equal to 1 to n dj comma 2, so summation I equal to 1 to n di comma 1. And this sum of degrees, that is just number of edges, right? So this is equal to m1. Like in the problem, the number of edges in the graph 1 is m1. And this is equal to m2. So the number of edges in this graph, the final graph would be m1 into m2. Okay. So there are n square vertices and m1, m2 edges. And the limits of m1 and m2 also are very small, like they are 1000. So m1 into m2 also passes. So you can just apply Dijkstra here. Okay. So is it clear on the logic and why it doesn't get TLE? So finally the TC of this would be just O of n square plus m1 m2 log m1 m2, right? So if I could show the code, n s1 s2 I'm taking. So s1 and s2 are starting points, and then m1 the number of edges, and I also made it zero indexing, so I decreased them. I have two adjacency list for both the graphs, and a vector of pair a1, like this stores the edges for the first graph, and this store is for second graph. And you might know that this is vector and this is set, and why that is, I'll tell you in a second. So these two stores the edges, that pair of L comma L, the edges. and this is the adjacency list. And I just took the input I comma m1, like this is for I equal to 0, I is in m1 I plus plus. So I just took the m1 edges as the input. If a greater than b, then swap ab. So I ensured that a is smaller and zero indexing, and then I just pushed adjacent one of a dot pushback b at b dot pushback a, and a1 dot pushback a comma b. And same for this second graph. Then I just applied Dijkstra here. So this DP is actually distance array. Like in Dijkstra, we have a distance array, right? So that is this distance array. And this priority queue in Dijkstra we have. So I inserted the first index, like the starting index, and the distance is 0. Distance of starting index is 0. And I just applied this Dijkstra here. This is very standard code, so I don't think you would have a problem in that. So this is just Dijkstra applying. And in the end, what I'm just doing is I'm iterating over all the edges of the first graph. Okay. So all the edges of the first graph. If second graph also has that first edge, like this x is an edge from, this is a pair. X is a pair. Okay. So if second graph also has that edge, is not equal to determinant, then ans equals min of ans, dp x dot first, x dot first. Like what this means is that the cost to go to one of the nodes of that edge, right? Minimum cost to go to that node. So I'll just take the minimum with that answer. And if answer is still equal to infinity, then C out minus 1 because there is no edge. And otherwise, I just print the answer. So if the answer is infinity, then they are telling us that if the answer is infinite, then print minus 1. So output one integer or minus 1 if it is very infinitely large, right? So yeah, that is the code. Okay, so is the code clear to you? All right. So yeah, that's all for that I did today. And if you have a doubt in any of these four, you can ask right now, or any general doubt if you have. Explain B code. Okay, sure. B was okay. This one, right? So the logic was that I need to check that. See, I think you would be checking n not equal to k case, right? Just when n is not equal to k. In this case, right? So if n is not equal to k, then logic was that we can actually take from I equal to 1 to n minus k plus 1. Like if there is any 1, if there is 1 in any of these indices, then the answer would be, sorry, if there is not 1, like if they are not 1, then the answer is 1. And if all of them are 1, then the answer is 2. So I just use the count function, not 1, then 1 if there. You got the logic, right? So I just counted all the ones from I equal to 1 to I equal to n minus k plus 1. So there's a count function for that. Like there's a count function which takes in begin iterator of the vector, n of the vector, and the element, the value that we want to count. And the n iterator is actually exclusive actually. So whatever we pass in here, that is not counted. So I just passed in like ARR plus 1, like for the first index, and ARR plus, I need to count till n minus k plus 1, right? So I give it n minus k plus 2 because it takes like half of an interval. So if you give it a comma b, then it will count like this, half of an half closed. So I give it this and 1. I give it this. Got it? Okay. So anything else? No. Okay, then we'll end this meeting now. I'll see you next time. Bye bye.